Good afternoon, everybody. Safe and sound back. Some of you, I'm very glad that everybody got out of the sea. So turn off Rudolph, clock interferometry.
All right, what's the proper distance? A little scary. All right. Thank you, Wolf, for having us back here, this beautiful place. I will be talking about long baseline atomic sensors, so instruments that don't fit in your average lab environment, and in particular, a 10-meter scale gradiometer at Stanford University and a 100-meter scale instrument that we are building at Fermi Lab. And other than being really tall, these instruments are also special in that they're clock atom interferometers, and that means they're using a different kind of atom and a different kind of atom optic. And I will tell you what the status is of these devices, how they work, and why we think clock atom interferometry is a really good tool to build such instruments. So the 100-meter device is called Majors 100 and is currently under construction at Fermi Lab, which is close to Chicago. And they happen to have this Minos building and access shaft from a now defunct underground neutrino experiment. And we have the privilege of putting our instrument in this existing shaft, which is about 100 meters deep. And so we will be able to distribute some atoms over this baseline and probe them with a common laser. And some of the science goals of this instrument is we want to demonstrate a prototype gravitational wave detector in the mid-band, so between the LISA and LIGO bands, as an intermediate step to a full-scale detector of a kilometer or much larger size, which could be terrestrial or in space. We also, with this instrument, want to probe for some ultralight dark matter candidates and test quantum mechanics on unprecedented length and time scales. And if you want to know more about anything in particular, we wrote a very, very comprehensive paper about this that should give you some more information on whatever you think is more interesting about this. This whole endeavor is made possible by the Majors 100's collaboration, which is an international collaboration of 10 institutions from the US and the UK. And you can see us there at last year's collaboration meeting at Northwestern, or a subset of us, I should say. And what's maybe surprising to hear is that it's kind of a unique collaboration because at least half of the members do not have an AMO background, but rather a particle physics background. And so we are trying to leverage their experience in building these really large-scale devices and operating these with very high uptime and so forth, and also their experience in sort of the engineering side of things of constructing and installing such a sensor. And what we bring to the table as the AMO groups is the underlying technologies. And in fact, much of the instrument hardware is being built at Stanford, for example, but also at Northwestern in Tim Kovacs's group. And they are responsible for the interferometry laser system. And our hardware will then move out to Fermi Lab as sort of an in-kind contribution to this experiment. But it's very much a very mixed collaboration. And we are also collaborating with the AON project in the UK, and in fact, even signed a very official agreement this year as hopefully a stepping stone to a larger network of such detectors that spans the globe in the future, or so we hope. So the apparatus looks something like this. So this is a CAD model of the Minos shaft. It's 100 meters deep, and there are atom sources distributed along that length. And to the right in that shaft is the instrument. We are basically installing a 100-meter vacuum tube, but it's not one long tube, but rather we have these 17 such sections of about 5-meter height. And every one of these sections is a vacuum tube that's magnetically shielded. and that has some supportive structure to it, and that each one of these is mounted to the shaft wall and can be aligned individually. And we're turning these 17 pieces into one 100-meter vacuum tube. Then the atom sources at the top, middle, and bottom, they provide ultra-cold strontium atoms in our case, and we do all the cooling and preparation steps in these atom sources. Then they are shuttled using an optical lattice to the vacuum tube, and then using what we call connection node chambers, where we have a lot of in-vacuum optics for another set of optical lattices, we can then launch these atoms in our 100-meter tube. So we have the ability to drop or launch atoms from these 3 locations. And then at the very top, we have a laser lab where the interferometry laser is housed. That laser beam is propagated in free space, but in a vacuum tube, over to the top of the shaft and is sent down the shaft and then retroreflected at the bottom. So what is the status of this experiment? We have received project status at Fermilab, which means that all the construction that has to happen at Fermilab is completely funded by the DOE, and the infrastructure engineering, so getting ready to install such a device and making a plan for the installation, but also for the access once it is installed. How do we get to the atom sources and work on the experiment? All this is quite mature. Here you see a picture of the top of the Minos building, and through the door on the left, there is the freshly renovated laser lab that is almost complete and ready for the optical tables to move in, which is always an exciting time for every lab. And the hardware for MAGIS is already under construction at Stanford and Northwestern with support from other contributors. And this will be installed in the not too distant future in the shaft. And here in this picture, you see looking down into the shaft to the right on this concrete, this is where this instrument will be housed. We plan to install the instrument by 2027. So not quite in time for the next FOMO, but the next time we're back in Crete, by the next time we're back in Crete, if things go well, we will have this thing installed, which I think is exciting to say. Yeah. So the large detector is still a few years away. However, we are getting extremely close to finishing up a 10-meter prototype version of the MAGIS detector at Stanford, which is built and shall remain at Stanford. This is a 10-meter version of MAGIS that has the full complexity of the large detector. The only difference being is it has a shorter baseline. So it's essentially a stack of 2 atomic fountains, and they're about 5 meters in height, and that gives you about 1.5 seconds of freefall time if you do a parabolic launch in these sections. We have most of the hardware together to build this instrument, and we're just finishing up the last pieces, and we're planning to put it all together and set it up in our 2-story lab later this fall. And this will act as sort of a pathfinder project for the MAGIS 100 detector, so we can test out sequences and do a lot of R&D ahead of time. But hopefully, of course, this will also be just a state-of-the-art gravity gradiometer in its own right. And we have lots of ideas for tests of fundamental physics that include, but are not limited to, the science ideas that we have for MAGIS 100. And just to give you an impression that we actually do have a lot of this hardware and we're fairly far along, here you can see the magnetically shielded vacuum sections that we built. They are vacuum tested, bake tested, the magnetic field has been characterized, and they are just waiting to be integrated. And here you see a model or a picture of one of our connection nodes, so not a model, but the real thing. So this is the connection node chamber that has a very complex inner life of in-vacuum optics. This has been aligned, then baked, and then verified that this alignment doesn't change when you bake this chamber. So this one is also ready to go, and we are now building the second one of this, and that's the final piece that we need to put it all together. We also have our retro chamber ready to go, which is a vacuum chamber that houses the retro mirror and actuators such that we can do Coriolis compensation as we use our machine. And last but not least, the heart of the experiment are these atom sources, and these have been around for quite a while, so we've been operating them for a long time. These are two self-contained complete atom sources, strontium experiments, and all the data and all the results I'm going to show you come from one of these atom sources. So in this talk, I want to do a quick recap on clock atom interferometry and remind everyone what are the differences and why do we make such a big deal out of them being different than conventional atom interferometry techniques? What are maybe some different kinds of clock atom interferometry, because it comes in a few different flavors. Then I want to tell you about a brand new thing that we came up with, which is a 3-photon clock transition, and a very specific kind of 3-photon clock transition, a collinear one. And at the very end, I'll show you how we turn this into a multi-photon clock atom interferometer. And I hope I can get you excited about the prospects of using this technique for such long distance sensors. We think this might broaden the scope of these devices quite a bit and might be a very useful thing to try. So clock atom interferometry is different from conventional atom interferometry. And when I say conventional, I mean Raman or Bragg, 2-photon transitions with 2 counter-propagating beams, where I'm detuned off a virtual level. In clock atom interferometry, instead, I'm using some kind of metastable level that has a fairly long lifetime compared to my pulse duration. And those 2 states can be linked in the simplest case with a single laser beam. And the sensitivity of such an interferometer comes from a different place. It comes from a clock phase, a differential phase that is evolved between these 2 states, the blue and the red state, that is given by the energy difference, omega A, between these states. And because it's an optical energy difference, this is quite a large quantity. And so you have a large differential phase, and the atom keeps track of how much time is spent in each state via these clocks. And if I do a Mach-Zehnder interferometer and it falls under the influence of gravity, then these clocks time the time spent in the excited state in the first half in the interferometer and to the second half in the interferometer. And if there is an acceleration, I get a phase that looks quite familiar to you probably. But instead of K effective, G times T squared, it's omega A over C. So in this case, it's a natural constant, just the energy difference. And I don't have any relative K from my 2 lasers. This is a different phase shift because it comes about because of the finite speed of light over the interferometer. So it's a relativistic effect that is present in a normal interferometer also, but because the ground states are so close together, it's usually completely negligible. But the fact that in a clock interferometer, at least in the simplest case, we don't have any intermediate levels that we have to detune from very far, we don't have that extra scattering, and that is very good for your pulse efficiency. And so clock atom interferometers have generally a pretty high ceiling for LMT enhancement, as we will see later. We want to turn this, of course, into a gradiometer where we have 2 such interferometers separated by a baseline L, and now I'm sending common laser pulses, 1 laser at a time, from opposite directions across this baseline. And in this kind of scenario, I have this freely falling atom and the clock rate of the atom keeping track of what is going on. So my atoms act as the inertial reference and the clock. And so these 2 interferometers act as phase references for each other. And this is how you can make a single baseline gravitational wave detector. And the leading order phase shift here is proportional to L over C, which is the light travel time across the baseline. And this is what gives you the gravitational wave sensitivity, but it is also proportional to omega A, the energy difference. And we have some ideas about searching for candidates for ultralight dark matter that may vary some fundamental constants like alpha or the mass of the electron in a periodic way. And then you'll be able to see this in this instrument. And as Enno pointed out on Tuesday, such clock atom interferometers, because of this large energy difference, are particularly sensitive to such effects. These interferometers are also proportional to N, the large momentum transfer order. So if I add extra pairs of pulses in the interferometer, and the one in the picture on the left has 2 extra pairs, I can linearly scale up the sensitivity of my detector with these pulses. And that will become a very common theme and important topic in this talk. So the cool thing about this and the main advantages of these techniques are that the laser noise is common mode suppressed because I'm sending a single pulse. So both atoms always see exactly the same pulse from a single laser. I already said we're very sensitive to dark matter candidates because of the large omega A, and then the large momentum transfer advantage is one of the most critical things when we look at the roadmap for a major style detector in the future. This is from our paper, the list of future potential extensions to what we're doing at majors and some estimations for where we will start and where we will end. And on the bottom right in this graph, you see a shaded region where the top line is sort of state-of-the-art performance of us starting out. And at the bottom, the dashed line is sort of an aspirational goal of how far maybe we could get down. And you will see that there are only 3 main ways of making my interferometer more sensitive. One is I can increase the baseline, which we're doing by going to the 100 meters. That, however, is quite tricky, and it's not very easy to extend that further. Every time you build a 10 times larger instrument, that comes with a lot of added complexity. You can also increase your phase resolution through your atom number or having less noise. Unfortunately, that scaling there isn't very favorable because it usually scales, at least classically, with the square root of the atom number. So you would have to have 100 times more atoms for 10 times the sensitivity. But last but not least, LMT atom optics, which have been demonstrated at a level of hundreds of H/K. We think that thousands or tens of thousands of H/K are in principle possible. And so you have this one knob where if you play your cards right, potentially you could get a huge enhancement factor. And since it is so difficult to build these large detectors on Earth, terrestrial detectors are all about LMT, and it's all about how many more pulses can I add to my interferometer. Clock atom interferometers come in a few different flavors. Here are 2 examples for these. They usually all involve some forbidden transition, which means a singlet to triplet transition. And while some of these transitions are strongly forbidden, others are sort of merely frowned upon, like this broadband transition that has a 7 kilohertz line width, where the excited state lifetime is actually rather short. It's 21 microseconds, and you might think that's way too short to do anything practically with it. But it turns out because you get much stronger coupling, you can get really, really high Rabi frequency, and your pulse duration is so short, on the order of 100 nanoseconds per pulse or less. So you can actually apply a ton of pulses within this lifetime and sort of manage this loss. And we think that this transition at reasonable laser intensity that you can buy can easily support 1,000 H/K. Due to this short lifetime, though, this is not really suitable for long baselines because your light travels along the baseline, and while it's happening, one of the atoms is already decaying from the excited state. So not a great technique for the long baseline. The narrow transition that we are very familiar with from optical atomic clocks and some of the best atomic clocks in the world, the strontium 1s0 to 3b0 transition, is extremely narrow and only exists in strontium 87, the one fermionic isotope. And it is only about 1 millihertz wide. So it has very weak coupling, and you are really straining to get much Rabi frequency out of it. You could get sort of kilohertz level Rabi frequencies. But we think because the spontaneous emission from that excited state of this transition is so low, this transition, although it's hard, it has a really high ceiling and can, I think, in principle support tens of thousands of H/K. So this is really useful for very long baselines and applications like gravitational wave detection. Just to show you that this really works, here are some previous results from our lab where we use the broadband case. And it is always fun for me to highlight this because of what a unique kind of transition and what a unique kind of tool this is. The broadband transition gives you so much Rabi frequency that you can take a narrow band mod, a narrow band strontium mod, so a strontium red mod at a temperature of 2 microkelvin, and apply many different pulses without any other cooling measures that you have to take. So you don't have to do any evaporative cooling. You don't have to go to BC or do any kind of metawave lensing. You take the cloud and then you get a pulse efficiency of larger than 99% average over this entire ensemble of atoms. No velocity selection necessary or nothing. This works so well, in fact, that we found that you usually, what you do is you set your laser to be on resonance with the 0 velocity class, and you talk to both arms of your interferometer always. So you have one laser and both arms of your interferometer interact with this laser and each get an h/k per pulse of momentum separation. And it turns out you are accelerating the arms of your interferometer really fast. And after about 200 h/k, you run into some issue where the laser that sits sort of centered in frequency will now start to be detuned from my arms because they're racing away from each other. So it's an interesting problem to have. But we found a creative solution to this. Turns out if you modulate your pulses with something that we call Floquet atom optics, then you can, for any given detuning, find a modulation frequency and a pulse duration that perfectly corrects for this exact Doppler detuning of the arm. And you can see this here on the block sphere. The trick is that we do a square wave modulation. So at a certain time, we flip the sign of the coupling, which flips the torque vector. And you can see on the block sphere, the first part of the oscillation is basically how much I would have missed the top of my block sphere. I'm trying to go to the North Pole, but because I'm detuned, I'm doing sort of an angled rotation. But if I turn around at the right time, I can get perfectly back to the pole. And so this completely resolves this issue. You have to make a unique pulse at every h/k, so every pulse is unique. However, we found some very clean analytical expressions for what the period should be. So this is very easy to implement, in fact. And then with this, we did a demonstration where we had atoms at 2 microkelvin temperature. We had 180 milliwatts of power, and we did over 400 h/k with this. And I think that's a super cool idea. The fact that you can have essentially one ECDL laser and a MOT, and you can get 500 h/k atom optics without any other complexity. So I think this is a really cool thing. And of course, it's really fast. Most of these pulses, the whole sequence is less than 50 microseconds. And we tried turning up the power a little bit because this is very low power, and we got up to 601 h/k. And if we had a working laser, we would have done more. But I've said this already last time. By next FOMO, we better be able to do a little bit more here. We think 1,000 h/k should be fairly easy to do. And I think this aspirational goal that many groups have had from realizing 1,000 h/k atom optics, by the next time we meet, I think there will be several groups doing 1,000 h/k. I'm quite convinced, including other groups at Stanford, including the group in Toulouse. I'm sure will be at this level, which I think is super exciting. So the narrowband case for clock atom interferometry is quite different, because the coupling is extremely weak in comparison. And it's interesting to think about what is the fundamental limit for such a LNT enhancement. And turns out there is a fundamental limit, and I've drawn this here for you. So you see on the x-axis, it is the LNT order applied, and on the y-axis, it's the actual enhancement, so n times the contrast. And anything you'll ever do on this transition is going to live in this gray area. And this is because you are fundamentally limited by the lifetime of the state, and then also by just off-resonance scattering from other states that are around, from other lines that are around, that you could accidentally excite. And even though that's very unlikely, once you do a lot of pulses, this can certainly happen. And so this is kind of the most that you could ever do on this transition. right? So the fundamental limit is something like 10 to the 6, but you would practically be very hard pressed to get there. And the problem is you get such low Rabi frequencies. If I only have a kilohertz Rabi frequency, it's really becoming sort of a timing problem. In majors, we think we have 5 seconds of free fall time for the atoms. So you have to build like a large instrument to get 5 seconds of free fall time. And then if I have a kilohertz Rabi frequency, even with exceptional pulse efficiencies of 4 nines, 5 nines, 6 nines, I will only be able to do a few thousand of H by K, and the lines end there because I'm literally running out of time. So I'm pulsing the whole time, but my pulses are so slow, I just can't get these pulses in, is the problem. If I have 10 kilohertz, then it's looking a little bit better, and maybe I can breach into the 10 to the 4. But of course, I have to have the right pulse efficiency. So 5 nines is really what's on the menu, what you would want to get from there. But you can see, yeah, this transition is really nice. It has this huge ceiling, but it's practically very hard to reach these Rabi frequencies. And then there's one more problem. This transition only exists for fermions and not for the bosons, and we only have one fermionic isotope in strontium. Bosons would have a ton of advantages that might even play into this and give you better pulses and higher pulse efficiencies because, for example, you can make a BC. BCs are, all things being equal, much more compact than a degenerate Fermi gas, which is great for your pulse efficiency. You could have more atoms because of the higher abundancy of certain isotopes. You wouldn't have nuclear spin, so level structure is much simpler. You don't have problems with cooling and straight preparation. They are much less magnetically sensitive. And one other fundamental thing, if you're ever thinking about doing dual species experiments, like equivalence principle type experiments or certain dark matter scenarios where you want to use 2 isotopes, you only have one fermion. So you have to do something to get this other isotope in play. People have been thinking about trying to get to the 3p0 clock state for the boson for a very long time. And there have been a few suggestions of how we can do this. One very straightforward, but not very practical thing is adding a strong magnetic field. This, in fact, was the method used by the Tino group to demonstrate the first narrow clock atom interferometer. But the problem is you need to apply a really strong field of thousands or hundreds of Gauss to induce a coupling that's then on the level of the weak line that we just saw before. So you need a strong magnetic field. So this is completely impractical for our 100-meter machine because we don't want to provide this field over the whole length, and it would only give you coupling that's just as weak as the fermion. There are also some 2-photon suggestions, but we found very interesting was a 3-photon transition that was proposed almost 20 years ago. And that particular transition is interesting to us because it is using lasers that you already have around. It's using the 689 laser to 3p1, and then a 688 laser to 3s1, and then comes down to 3p0 this way. And when we say 3-photon transitions, we mean that we don't go into the intermediate states, but rather we turn this into one coherent transition from 1s0 to 3p0. So the problem is, though, with this transition, it turns out, because of selection rules, you cannot send all your light from the same direction. And if you write down the coupling, which is the product of the individual couplings divided by the detunings, as we would expect, you find that the coupling scales with the vector triple product of the polarizations. So the polarization vectors, if they span a volume, you get a lot of coupling. If they don't span a volume, then your coupling is 0, and this transition just doesn't go. And the only way to make this transition go is to send at least one laser from a different direction. And in fact, in the Schreck group in Amsterdam, they did just this around the same time that we were getting our results, and they are doing it in this way where one beam is sent from the other direction. However, that doesn't work for us because we have this long tube. We want to send our interferometry pulses just from one direction. So this isn't quite working out for us. What we want to do is we want to have something like a XXZ polarization for the 3 light components and send everything along the Y direction, for example. And turns out you can do this if you add a magnetic field to the mix. And you can see this here in the level diagram. I'm breaking the degeneracy in the 3p1 state. So now these two paths to the left and to the right they would normally destructively interfere in the 3s1 state. But once I lift the degeneracy with my magnetic field, that is no longer happening. And you can see this expressed here. If delta omega b, which is my Zeeman shift, if that is 0, this also is 0, right? But with this magnetic field, which is a constant magnetic field that you apply, you can make this transition go. And then you can apply your light from the same direction, from the same fiber, all in a single pulse at a constant magnetic field. So this is a mathematical way of seeing why this works, but we can also visualize it with the angular momentum wave function. And this is really cool. We learned a lot about some of these clock transitions, trying to figure out what's even happening here, because there are some counterintuitive things that happen when you do a singlet to triplet transition. Usually when I do an allow dipole transition, the polarization of my light field wiggles a certain way, and then I can couple an s orbital to a p orbital exactly in the direction that my light was oscillating, right? So this is my expectation. And this is in fact happening in this picture where the spin states are the colors and the spin projections are the colors, and they're color coded this way. And if I have a, let's say, a Z polarized green light field, I can couple a p orbital along the Z direction with an s orbital, and that's an allow transition. But the very first photon, the 689 nanometer transition, there the situation is very different because this transition isn't allowed at all. My light field is polarized at x, and I'm trying to wiggle, and the response of the atom is completely perpendicular to my excitation. And this is because this transition only goes because of spin orbit coupling indirectly, right? And so now when I do this, I just like, without loss of generality, I've decided I'm going to start with a polarization in X. Then the 3p1 state looks like this. And then I have two routes that I can go through the 3p0 state. And as you can see, no matter which path I take, I need X, Z, and Y, or X, Y, and Z. So I need all the directions for my light. I cannot send all my light from the same direction. But adding the magnetic field changes the shape of the angular momentum wave function in 3p1, and I'm doing sort of a wave plate-like rotation of that orbital, and then that makes this transition go, and I can now choose XZ polarization, for example, to make this transition go. And this is what we did. We predicted where this 3-photon resonance should be. We have our lasers locked to a frequency column, which was very nice. And of course, many of these transition frequencies are extremely well known because of all the clock business and all the clock people who have worked with these atoms before. So we could predict, and this is the shaded region, we predict the AC Stark shift should shift the resonance to this value by about 100 kilohertz. And this is exactly where we found this 3-photon transition. And yeah, this really requires all the 4 fields. This goes away if you take away the magnetic field and so on. And we can do a Rabi oscillation there. And what's really cool is we see Rabi oscillations with frequencies of up to 50 kilohertz. So substantially stronger, even just at first attempt, substantially stronger than on the narrow line. And this is using just a 10 Gauss magnetic field and less than 10 milliwatts of laser intensity. And you may say, well, this is a very damped Rabi oscillation, but this is only because we had so little laser intensity or so little laser power. We were just focusing our beam. And if you had more power, you make the beam larger at the same intensity, then there will be no such damping. And in fact, it will be a nice oscillation. Some more technical details. It's interesting to parameterize this coupling as the ratio of the Zeeman shift to the first laser detuning. And then you see here that there are sort of 2 regimes where you can drive this transition. And we introduce this beta factor as the ratio. And when this is 1, then you're basically resonant with the single photon transition to 3p1, m plus 1, which you don't want. So you have to stay away from this a little bit. But you can see the model here, which has no free parameters. So this is just this is the effective 2-level coupling that we derived and our data. And they agree very well, which means we really did make a great effective 2-level system, and there are no other processes going on. In a different parameterization, we can sort of divide out the magnitude of the scaling such that we can then sort of connect it back to the rotation of the orbital of the angle, and then you can see that again we find very good agreement with theory. And of course, once you have a 3-photon pi pulse, you can make a 3-photon atom interferometer, and that's exactly what we did. So this is a first demonstration of a multi-photon clock atom interferometer, where every pulse is a 3-photon atom optic. And here we did, in just first example, a T, so this is a Mach-Zehnder sequence, and we did a T of 200 microseconds, so just a larger time compared to the intermediate states, and we don't see any contrast decay with this T. And this is a proof of concept for using such a transition in a large-scale detector like MAGES. And what that would allow us to do is use all the bosonic isotopes in MAGES if we wanted to. So it could be a bit of a game changer because you now don't have to rely on the fermions. And the other tempting thing is now to think about, if I get really strong coupling, if I get 50 kilohertz Rabi frequency, maybe 100 kilohertz Rabi frequency, I might be practically able to do way more pulses with this trick than on the narrow line. So practically, this might win out, but the limits are still to be studied. If you are a keen observer, you might complain because about 10 slides ago, I told you that for the 2-photon transition, you have this intermediate level, and that's bad because you get scattering from it. And now I'm trying to sell you 2 intermediate levels. So, but we think this still works because what you can do in this 3-level transition is I can put all my laser power in the middle laser in 688. I put all my intensity there, and my coupling is a product of all the intensities. And then I am twice removed from scattering from either the excited or the ground state, and it should suppress that loss rate substantially. So we think that even though we have these intermediate states, we think that the upper limits should be more comparable to the other clock atom interferometer. And another cool thing is even the light shift, the AC stock shift that you get, turns out if you pick your detuning for the 688 laser just right, you get to compensate this. We laid this out in the supplemental if you care about such technical details. We think this is a very exciting thing because we've been thinking about fermions for years for these detectors. And I think it would be really cool if we could sort of switch it up and enable dual species operation and maybe just all out bosonic operation for such a sensor. So I hope you're taking away that we're working towards some very, very interesting devices at Stanford at Fermi Lab. And these strontium clock radiometers are not unique. There are other experiments like this. So the Aeon project in the UK, for example, has a very similar science program and very similar technologies. We think that clock atom interferometry has fundamental advantages that are very exciting. And yeah, we demonstrated this new technique that enables this bosonic isotopes and dual isotope operation in such sensors. Before I let you go, we randomly had a very productive year and put another paper out on the archive, a completely change of subjects, but if you work with spatial light modulators in any capacity and you like to generate beams with very high efficiency and very low error rate, then you may be interested in the algorithms that we have put out in this paper. So this is a theory paper about finding appropriate phases in a very convenient way. And we think that it just gives you lower error profiles and uses much more of the light. And you can find it on archive. And the source for this is also open source and is on GitHub. This effort was led by Hunter Swan. And so let me thank some of the people who work on all these projects. TJ Wilkerson and Megan Nantel were instrumental in all the broadband interferometry results, and Benjamin Garber and Yijun Yang have had enormous contributions to the design of the 10-meter and the 100-meter machine. Sam Carmen and Benjamin Garber have worked on these cool new 3-photon results. Yeah, and also, I have a long list of MAGES 100's collaborators, and I want to thank especially those people whose name I don't have on the slide. All right, thank you very much.
Okay, first question.
Thank you very much. Very beautiful results on the three photon transition. In the interferometer that you started, that you tried, why did you stop at these very small times? I mean, just to highlight the challenge, is there something there that...
All the interferometer work that we've always been doing has always been horizontal. So the atoms just fall out because we said, let's keep the other configuration for when the setup is complete. So just out of convenience, we have applied the pulses horizontally, right? And so it's just a technicality.
Very nice talk. I have a question about the three photon process. So if I understood correctly, the magnetic field that you have to apply, the additional magnetic field, was it transverse to the direction of the laser beam? Because if so, is that a practical issue for your long baseline or?
So the magnetic field is, you can see it here, it's in Z direction, right? So it's a transverse field.
Mm-hmm.
And in fact, the Major's instrument has bias bars all along the 100 meters to provide an arbitrary field transverse to the beam of any orientation. So that's already required for this other single photon transition. So we have that capability to do that.
I see. So, but you have both the launch field and in addition, what you were just saying, is that correct or?
Yeah, we don't even, the usual bias field isn't, for the clock transition isn't necessary. But for example, in the prototype, we have a large solenoid wound around the tube sections as well. So you can in principle apply an arbitrary field up to a certain strength in this device.
Right, thank you.
So other questions? So I don't see other questions. Thank you very much, Jan. And thanks